Welcome. This is the Cisco CCNA ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Welcome. In Module 1, we are looking at the Single Area OSPF v2 concepts. So this video is going to be talking about what OSPF, how does it function, key characteristics, things of that nature. Also looking at OSPF operations in a single area and some packet types. So first of all, let's look at the features and characteristics of OSPF. OSPF is a link state routing protocol that was developed as an alternate to RIP. OSPF is open source. It has significant advantages over other routing protocols such as RIP. The fact that it's a link state routing protocol, that means it will use the concept of areas. A network administrator can divide the network into routing domains, which are more like spheres of control, into distinct areas to help control routing and updating of traffic. A link is an interface on a router and the network segment that connects to routers, or a stub network such as a LAN. The information about the state of a link is known as a link state. Basically, all link state information, including the things like network prefixes, length, and the cost, are shared with other routers. So this module will cover basics on OSPF, specifically on single area OSPF, the implementation, and the configuration. A big takeaway is link state basically means that all routers will have a map, per se, of all other devices on the network. It builds a map for connectivity overall on the overall network. That means if the network changes, a route goes up or a route goes down, all other devices, all other routers have to be sent updates in terms of what the different link states are. So that makes this a little bit more complicated than other routing protocols. But the fact that all routers have a map makes things a little easier too. So it just kind of depends on circumstance and which routing protocol is most appropriate. And we'll get into those a little bit later. Alright, moving on. All routing protocols will share similar components that they use to exchange routing information. So these routing protocol messages that are used to exchange information help to build the data structure of the route maps or the routing information. So routers running OSPF will exchange messages to convey routing information using 5 specific packet types: a hello packet, a database description packet, a link state request packets, a link state update packet, and a link state acknowledgement packets. One thing that I do not like with the new material is it doesn't really give us a nice description of what those packet types are. So the hello packet are packets that are sent over a period of time to all interfaces for the purpose of establishing and maintaining neighbor relationships. Basically, the hello packet are a multicast, sent via multicast on the network, having a multicast capability that enables discovery of the neighboring routers dynamically. The database description packet basically is at the time of the adjacency being initialized. When one router learns about a neighboring router, that's the adjacency coming up, these packets are exchanged. The packets are describing the topology of the database content. Basically, what the router knows about the topology, it will put that in a database, send it to its neighbor when there's an adjacency formed. The database may be described by using multiple packets, not just a single packet, because again, all routers will eventually have all the information that all other routers have in a link state, So they do this by exchanging the database description packets. It is important to note that with OSPF, there will be a master router that controls everyone else. And the master router will be known as the master. All other routers will be known as slaves. The database description packet are sent by the slaves after sending the database description packet by the master. So the master will have as complete information as possible, then it will update all the slaves. Next would be the link state request packet. So as a router may find part of its topology database are out of date, after a database description packet exchange with the neighbors, the link state request packet is utilized for requesting the pieces of the neighborhood database which are more up to date. So essentially it may have pieces A, B, and C, and A and B are up to date. C is out of date. The link state request packet will be sent to say, hey, I need this specific information. Next will be the link state update. And basically the flooding of a link state advertisement is implemented by these packets. It's a collection of link state advertisements and are carried by each link state update packet, one hop further from the origin. So basically a packet may be included by several links being sent. Normally you'd want to send a link state update packet just to your neighbor. So that is the one request past your neighbor. Basically, if you know your neighbor, and your neighbor will share its neighboring information, and its neighboring information will share it, you can slowly build a network map based off of just the update packets. Lastly will be the link state acknowledgement packets. The reliability of flooding link state advertisements is made by explicitly acknowledging the flooded advertisements. The accomplishment of this acknowledgement is done through the sending and receiving of the link state acknowledgement packets. Basically, a single link state acknowledgement packet is used to acknowledge multiple link state advertisements. This is the type of packet that will be sent to understand that I am receiving updates, I'm receiving information, and you will acknowledge it. Or the OSPF routing protocol will acknowledge that it received update packets using the acknowledgement packet type. So those are our 5 main types of packets used by OSPF in exchanging information. So one issue is the database description. There's multiple databases. So there's the adjacency database, which has the neighbor table. There is the link state database, the LSDB. This is the topology table. And there is the forwarding database, the routing table. So essentially, if you want to look at the different databases, you have to run a few different commands. We have a lab going through all of this, so we'll do that in Packet Tracer a little bit later. But for now, if you want to view the adjacency database, you would do a show IP OSPF neighbor. If you want to look at the topology table, you will do a show IP OSPF database. If you want to look at the forwarding database, it would be a show IP route command. So each database has different show commands so that you can see different types of data. So the router will build the topology table using results of the calculations based on a shortest path first algorithm, an SPF algorithm. The SPF algorithm creates a tree by placing each router at the root of the tree and calculating the shortest path to each node. The tree is then used to calculate the best routes. And then that's what's actually forwarded. So the link state operation, in order to maintain routing information, it has to complete a generic link state routing process to reach each state of convergence. The state of convergence is going to be where all routers have information on all other routers. There are a few link state routing steps that are completed by a router. Each router will establish neighborhood adjacencies. They will exchange link state advertisements. They will each build a link state database. They will each execute a SPF algorithm. They will each choose the best route. They will also then share that information with their neighbors. And again, this is just a generic link state routing process that each of the routers will go through. Now let's look at, to make OSPF more efficient and scalable, there's a hierarchy routing using areas. We can have a generic single area with OSPF being area 0. We can also have a multi-area called multi-area OSPF. And this OSPF is implemented using multiple areas in a hierarchy fashion. All areas must connect back to the backbone, what's called area 0. Routers interconnecting the areas are referred to as an area border router, ABRs. The focus of this module is only on OSPF v2 using single area. Also, typically getting more in depth with the ABRs is not done at the CCNA level, so do keep that in mind. Just for completeness sake, here we have two other areas. We have area 1 and area 51, and we have two ABR routers, R1 and R2. Again, everything connects back to area 0. The hierarchy topology being looked at here basically allows for smaller routing tables. It will reduce the link state update overhead. Basically, you stay within your area, so area 1 will have its routing updates, area 51 will have its routing updates, and it will also reduce the frequency of the calculations, because again, you're only working within your area. So we were looking at OSPF v2 for the most part. Well, there is an OSPF v3, and that is specifically for IPv6. It will exchange router information to populate the IPv6 routing information with the remote prefixes. Again, note that with OSPF v3, address family features, including support for both IPv4 and 6, are beyond the scope of the CCNA. OSPF v3 has the same functionality as v2, but uses IPv6. So the same type of packets, same type of advertisements and databases, same thing. Same type of SPF, but again using IPv6 information, not IPv4. OSPF v3 has separate processes from its IPv4 counterparts. So you can have OSPF v2 with one process ID, and you can have a OSPF v3 with a separate process ID. The processes and the operations are basically the same, but run independent of one another. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.